how can we solve the Q-curvature optimal partition problem? We are going to follow the Terracini, Conti, and Versini approach. So this approach is given by using some weakly coupled systems, I will tell that what that is, and a phenomenon that comes from physics, that is phase separation. So can we solve the optimal partition problem? How can we solve the optimal partition problem? The answer, surprisingly, comes from physics. Let's say physics have the answer, have a hint. And what is the main idea here? The main idea is the following one. If we consider this kind of partial differential equation of elliptic partial differential equations system, we have here a kind of Yamabe type problem plus some coupling terms. And what does this model? This model, Bose-Einstein condensates of two different hyperfine states which are overlapping in space, like here. Here we have actually two states. So they are overlapping in time. And if we can consider this number lambda to be positive and to be negative. This is the cooperative case, and this is the competitive case. So in the competitive case, both of the states are competing with each other. What happens? What is the interesting phenomenon here? The interesting phenomenon here is that when we have the competitive case, if lambda goes to minus infinite, this competition of the states is going to act in such a way that the states tend to separate to each other. So as lambda goes to infinite, this competition is stronger, and for lambda, really, if the absolute value of lambda is really, really big, what we obtain is that actually these states are separated with disjoint supports. So what we have here, if we consider the supports of these functions, this is on Rn, we are actually, let's say, we are actually giving some kind of, let me make a draw. We are giving a kind of partition to Rn into two pieces. And these two pieces has empty intersection. So the idea here was, if we consider two equations, we obtain two solutions to this problem having disjoint supports, and this disjoint support give a partition to Rn. What happens if we consider more solutions? With more solutions, can we obtain another kind of partition with, let's say, L parts to Rn? And can we still obtain solutions having this phenomenon here, which is called phase separation. So this question was posed by Conti, Terracini, and Fezzini, and what was their approach? Their approach was to consider weakly coupled competitive systems on Rn. This is, we consider a kind of Yamabe problem on Rn plus coupling terms in such a way that this lambda is negative and this alpha is given by this number. So we have here a weakly coupled competitive system with critical exponent nonlinearity and also critical exponent coupling terms. So considering these systems, if we can obtain a solution, let's say U equals U1 to U L, these are L equations, in such a way that each of these are non-trivial and each of these is positive. If we take these guys, this parameter lambda tending to minus infinite, let's say this is a solution given for a fixed lambda ij. Okay, so if we consider all the solutions, if we consider solution to this problem, fixing L, these lambdas, and also if we look for solutions Ui lambda ij having least energy, in some sense, maybe the least energy is not attained in the general case, but imposing some symmetry assumptions, it will be attained. So if we obtain this, then we are going to obtain the phase separation phenomenon. If we consider lambda ij going to minus infinite, what was their approach? The approach of Conti, Terracini, and Fezzini was to prove that these solutions are going to converge in some sense to some solution that I will call U infinite. And the approach is proof that each of the components are positive, they have disjoint supports, and they solve. They have disjoint supports, and if we take ij equals to the interior of the support, then this collection is going to satisfy the optimal partition problem. That is, we are obtaining a partition of Rn in L domains in such a way that these guys here solve a Dirichlet problem with least energy, and if we sum all the energies, we are going to obtain the least average of the least average of all solutions among all solutions of this kind. What was the approach of Clapp, Saldaña, and Sulkin? The approach was, as we cannot attain the least energy in general, we are going to, they impose some symmetry assumptions. That is, they give a closed subgroup of the group of isometries in such a way that the dimension of each orbit is at least one. With this, the solution to the gamma invariant optimal partition problem is attained. And what is the gamma invariant partition problem? That is the optimal partition problem. That is, if we have here a solution of this problem, a partition, then UE is gamma invariant. That is, UI composed with some element of this group of isometries is going to give this, and also each of these guys is gamma invariant. That is, if P lies in this guy, the entire orbit will lie also in this domain. And what was the sketch of the proof? The sketch of the proof was this one, Conti, Terracini, and Bettini's approach. But instead of looking for solutions on Rn without symmetries, they consider, let's erase something like this, they consider the space of all gamma invariant functions lying on this space. This is the closure of the C infinite functions with compact support under a suitable norm. And the suitable norm is given by the conformal Laplacian on Rn, which is the Laplacian, the common Laplacian. So the question was, can we obtain this result for Q curvature problems?